Assalamualaikum and a very good day to the evaluators of 44th edition SEDEX for final year project. So my name is Zharfan bin Hisham and I'm from Chemical Engineering Department. My final year project will be about esterification of acetic acid to methyl acetate using zirconia supported on SPA15 catalyst. So basically, esterification process is a reaction process between carboxylic acid and alcohol in order to produce ester and water as byproduct. So my final year project will be about the reaction between acetic acid with methanol in order to produce methyl acetate. So few applications of methyl acetate in the industry include in the manufacturing of lacquers, coatings, nail polish removal and also dye. So there are few limitations from current catalysts used in the esterification process from published literature. So the limitations include corrosive nature, difficult to separate the catalyst for reuse purposes, produces side reaction for homogeneous catalysts, while for heterogeneous catalysts like embellis and also indium type of catalysts, they have small pore distribution on the catalyst. With the mentioned limitations from current catalysts used, so zirconia metal oxide supported on mesoporous SBA15 comes into the picture with its own advantages, like having strong acid sites and also large pore distribution. So there are three primary objectives for my final year project. The first one would be to synthesize zirconia supported on SBA15 from published method. The second one would be to characterize the catalyst from few characterization method. The third one would be to predict the conversion of acetic acid and optimization of esterification without going through experimental process, but only using response surface methodology or RSM in design expert software. The studied variables would be molar ratio of the reactants, catalyst loading, and reaction temperature. Moving on to literature review, so I would like to highlight on the below part of the slide, which is the esterification of acetic acid to methyl acetate but using different type of catalysts. Although the names of the catalysts are quite similar, each of the catalysts have its own uniqueness in terms of the acidity and pore distribution. Like an example, embellis 36 have the highest acidity and quite large pore distribution, which then produce the highest acetic acid conversion at 69% compared with other catalysts. So to provide an overview of RSM, it is basically a multivariate technique for analytical optimization of operating parameters. It will require the user input of dependent variables, which is the conversion of acetic acid, and independent variables, which is the reaction temperature, catalyst loading, and molar ratio of reactants. It is an experimental design from matrix composed by different level of variables. Like an example, it will require user input of 20 experimental runs for central composite design, covering from low value to high value for each factors involved. So after catalyst preparation and characterization, RSM method will follow through in order to determine the optimized operating parameters for esterification process. However, RSM will require user input for both independent variables and dependent variables. So for independent variables, central composite is chosen to be the experimental design. The total number of experiments is at 20 runs, ranging at different level of arrangements for each involved factors. So for dependent variables, the aim is to estimate the conversion of acetic acid from predetermined center point conversion of published literature. So this can be done by firstly compare zirconia SBA15 with other current catalysts used in terms of acidity and pore size distribution. The second step will be to conduct catalyst similarity identification in order to choose one catalyst as basis. So the first and second step will be further explained in the next slide. Then the third step would be the conversion results utilization from catalyst basis due to its expected similar catalytic activity. The fourth step will be the data validation and analysis from ANOVA in Design Expert software. So this would be the catalyst comparison table for Zirconia SBA15 with other potential catalysts in terms of its active sites, pore volume, and surface area. So in order to choose the right catalyst basis for my FYP, since there will be no real experimental process being conducted, so Embellis 70 will be taken as the first basis due to its closest acidity. However, the pore volume of Embellis 70 is very low compared to Mesoporous SBA15. Thus, the catalyst basis will be rerouted to Embellis 16. Although the acidity of Embellis 16 doubles the Zirconia metal oxide, the pore volume and surface area of Zirconia SBA15 predicted to balance out the high acidity of Embellis 16, thus considered to be a reliable catalyst basis. And then the conversion from published literature using Embellis 16 will be used as the user input for the conversion. So this would be the results and discussion for catalyst characterization. What I can conclude is that the formation for both SBA15 and addition of Zirconia onto SBA15 are confirmed from comparison with published literature. So this includes the catalyst summary in terms of its surface area, pore volume, and also the acidity of the catalyst. So this will be the RSM empirical model produced after the user input into the software. So from high value of R squared and adjusted R squared of more than 0.95 indicates that the model is significant and also the user input is reliable. So for each factors involved in the esterification process, A represents the reaction temperature, B represents the catalyst loading, while C represents the molar ratio of reactants. So all the factors have significant effects towards the esterification from the high F value and low P value. So catalyst loading have the highest F value, which tells us that it have the highest interaction effect towards the esterification process itself. So this would be the 3-dimensional and 2-dimensional surface plot for RSM. So these figures are actually useful in order to visualize the interaction effect among factors for the esterification process. So the most left figure is the catalyst loading versus reaction temperature. So it is followed with molar ratio versus reaction temperature, and also the most right figure would be the molar ratio versus catalyst loading. So the highlight point would be when there is a change in catalyst loading, as can be observed from first factors and third factors interaction, the curvature effect and the wide gap between the surface lines becomes more observable. This indicates that catalyst loading have the highest interaction effect and also becomes the most influential factors. So this would ultimately make an impact in the conversion process. So after studying the interaction effect among factors, this step is crucial in order to optimize each of operating parameters involved in esterification process. So in optimization, it requires boundaries set by the user. So for factors involved, the boundaries set are between range as tabulated in previous slide, while the conversion of acetic acid is set at maximum. The importance for factors is set at 3, while the conversion is set at 5. So the software generates 10 solutions, and the chosen optimum solution would be as highlighted in the orange box, where the temperature is at 75 degrees Celsius, catalyst loading is at 0.03, while the molar ratio of reactants of acetic acid to methanol is at 1 to 3.8, and the obtained conversion is at 0.785. So in conclusion, all the objectives are fulfilled through the proposed methodology. So that will be all from me. Thank you very much for listening.